Hey everyone, this is Matt with Learn Everything About Design, and in today's video we're going to be modeling a triple clamp for the GPZ project. Now if you watched the last video, you saw where we talked about what we were doing, why we were doing it, and how. And this video is where we're going to go through that how portion. So we're going to talk about measuring the original triple clamp, 3D scanning it using the Revopoint MetroX that we have here, and then we're going to walk through the design in Fusion. We're going to make our basic detailed drawing and send it off to PCBWay, who's the sponsor of this video. So at the end of this process, we're going to have a nice CNC machined black anodized triple clamp back from PCBWay, and we're going to go through all the steps in the process. Now, keep in mind, if you don't have access to a 3D scanner, you can still design parts like this as long as you can gather all the critical measurements that you need. So we're going to talk about some of the critical measurements as it relates to a triple clamp, and then we're going to go through the process of using the MetroX and 3D scanner. All right, so the first step in this process is obviously to get some measurements. Now you can do this the old-fashioned way with some calipers. You can also take this and trace it on paper and get pretty close and use 3D printing like the pieces that we have here as a final test to make sure that everything fits. Now we're going to go the route of using a 3D scanner, and if you do have access to tools like calipers, then you should have at least some understanding on how to use them, but make sure that you do get as accurate as possible with the measurements, so that way you have at least good references going forward. So what we're going to do here is we're going to take a look at using the MetroX from Revopoint, and we're going to take a look at both full field mode as well as laser scanning mode. Now it is important to remember that with laser scanning mode, we are required to use marker dots, and the best thing for us to do is to capture what's called a global marker file. This is going to pre-capture the location of all of the different marker dots that we see, and we need to make sure that we have at least 4 to 5 visible at all times. Otherwise, we're going to run into issues when we go to transition to the side of the part. And really what we're looking to do is we're going to capture as much detail as we can. We want to get into the bores where it holds onto the forks, because that's the area where we really want to focus on the overall dimensions to make sure that it's accurate. So I'm going to be doing this in handheld mode, and it's always a good idea to set up a new scan and make sure that everything is set appropriately. Now, this is just on my wooden workbench. It's pretty messy, and I've got the sort of the marker dots and everything around it. If you have the ability to have a large, flat, rigid sheet, not a magic mat, but a rigid sheet with marker dots on it, that's a good thing that you can sort of pre-capture all those global files. For us, I'm going to increase the exposure a little bit, and I'm just going to start to capture. So even though I'm using smaller marker dots on this, the software still treats them as the larger marker dots, which is unfortunate. So that way when we go to scan and it goes to remove these marker dots, it's going to treat them like the large ones. So I think that Revopoint is working on that, and hopefully they'll get that sorted out. It's still okay, but we just want to make sure we don't stick them too close to the edge. If they're too close to the edge, then we're going to start to lose some information when we scan. We're going to complete that. And once we have it, we have cross-line accuracy, preset point distance. We don't need a ton of detail. 0.3 millimeters is going to be fine. The object type we're going to set to metallic shiny. And really all this does is it's going to change the intensity of the laser. We can also change the scanning distance if we want it to be a little bit larger. We can play around with the scanning distances. For us, however, cross-line, high accuracy, metallic shiny, we're going to hit cloud scan and get started. The benefit of using global markers is that we can scan quite a bit faster. I do want to play around with my exposure value a little bit. Looking at the preview window, I want to make sure that what I'm seeing there looks pretty good. But once we have our global marker files, we should be able to go pretty quickly back and forth. Now, you'll notice the preview is jumping around a little bit. That's okay. All we really care about is that the capture window is going to be nice and clean. Now, one big thing that we have to make sure we remember with laser scanning is we want the preview on the screen to be bright green. Now, anything that is red or pink or this sort of like more muted green has the ability to get filtered out pretty easily when we actually start to process the scan. And that's not a good thing. We want to keep as much data as possible. So for the best chance of having a good, clean scan to work with, make sure that everything that you scan turns bright green, and then you'll be sure to get the best result possible. But once again, if it's not bright green, that doesn't necessarily mean we can't use it. We just have to be careful with our settings when we're dealing with processing. Now, one other thing to note is in laser scanning mode, and I think this is something that Revopoint is working on. In laser scanning mode, especially with shiny objects, we tend to get a lot of sort of these residual points floating in air above our part as well as below. Those get filtered out pretty easily, and I believe that they're working on a Revoscan version that will sort of help the preview on the screen to look a bit better. Right now, this looks really messy. Unfortunately, that's just kind of what we're dealing with. But again, part of it is because of the shiny object. If I had used scan spray on this, it would be a different story. But for right now, we're just going to continue to go with it, moving back and forth until everything we're interested in is that bright green color. At any point in time, because we are using global markers, we can pause and we can interrogate this. But another thing to keep in mind, the two depth cameras, when we roll over an edge, you don't want one to be above the edge and one to be below. So if you've got a part like this that's kind of wide, you want to make sure that when you roll over that edge, that you're doing it with the scanner in this orientation, and you're not turning it 90 degrees, because then one depth camera is not going to be able to see the lines. So again, when you roll over the edges, you want to make sure that you keep it in line and you're giving it the best chance to capture everything. So you can see here that we're losing a little bit of tracking. The markers work well until you get to about 15 degrees, and then it starts to lose tracking on them. That's obviously problematic. We're going to also take a look at doing this with full field mode. Now, the tracking on full field mode can use global markers, and it is a bit quicker. So I'm going to go ahead and pause this and take a look at the results. And again, it's really hard to see. If we zoom in, we can see the clamp in there, and again, a bunch of that stuff floating around. Partly it's there because we're dealing with a shiny object. I'm going to go ahead and complete the scan, and I'm going to use the same global marker file to do a full field scan. So we're going to go to New Scan. We're going to go full field. And then we want to set this to global marker tracking. So we'll take the last frame that we captured, full field, global marker, and we'll do a cloud scan. All right, so when I pick this up, make sure that I rotate the view, and we're going to get started. So again, with global marker alignment, this goes quite a bit faster in full field mode and in laser mode, because we can jump around because it knows where all those markers are. So it simplifies the process. Now, since our preview is blue, I'm going to increase the exposure, kind of work my way back and forth. And then come up over the edge. All right, let's go back this way. All right. Now this scan's not going to be nearly as clean as the laser scan. The preview looks quite a bit better. All right, we're going to go ahead and pause that. Just take a quick look. It looks a bit messy, but I think we're going to get to filter some of that out. I do want to try to get into the bores a little bit more. It's going to be tricky. Let's see if we can just capture something in there. It's blue, which means it's underexposed. So I'm going to kick it up, see if I can just get something in there. All right. All right, we're going to go ahead and complete that. And I'm going to do a new scan. So we're going to do a new full field scan on the bottom. This time we're going to use feature tracking. And I want to get the exposure just before it starts to turn red. Now there's a high probability that we're going to lose tracking just because we don't have a lot of unique features. There's symmetry that we're dealing with. You can already see there it lost tracking. And this is one of the problems that we have when we're using a setup where we don't have markers. So I'm going to go ahead and put some markers on the bottom. Since what we're doing, we don't actually need any of these threaded holes. It'll be a good opportunity for me to put some markers in those areas because they are somewhat flat. All right, let's take a look at that. So it looks a bit messy. Again, some of that's going to get cleaned up in processing. I think we'll go ahead and complete it. While we have it all set up before anything moves, let's go ahead and capture global marker laser tracking on the bottom, get as much detail and data as we can. I'm going to leave this bottom one as general object simply because it's not very shiny on the bottom. It's still very much cast. Need to increase the exposure and get going. So I know I mentioned this in the review video, but laser scanning, even though the frame rate is much higher, is going to feel a lot slower than full field mode. And part of the reason for that is full field mode is going to bring in millions of points in the area that it's viewing, whereas the laser scan mode, either the cross line or the parallel, are only going to bring in scan data where the lines are touching. So even though we're capturing more frames per second, we're bringing in less or fewer points per frame than we are in full field mode. Now, the benefit here is going to be increased accuracy. So the full field mode and the laser line mode are both going to be extremely accurate, but the laser mode is supposed to be better at getting deeper into crevices and pulling out finer details better than the full field mode. For a part like this, it really doesn't need the laser scan because the only thing that we're really interested in is just pulling out the locations of the clamps and the stem. I will also note, because I've taken this bike apart and put it together so many different times, that the offset between the forks and the stem is a little bit off on the bike versus the clamp. Now I'm going to match the clamp dimensions because I think when you take the top triple off and it's sitting on the ground, it actually flexes the forks a little bit. So I'm going to just try to match the triple clamp since I know that's the dimension it should be, rather than trying to match what the bike is currently sitting at. So when we're doing this, again, I can't stress enough that the bright green is what we're looking for. So anywhere that you are capturing and you need that information, you want to make sure that it's bright green. If it starts to get lighter green or pink or red, then when we go to process this in Revoscan, what's going to end up happening is that data can easily be dropped. And if we need that information, if it's important, then it can be much harder to get, and it's going to have more variations in the points, which means that it's not going to be as accurate. So spend the time to go back and forth and capture everything in green. Part of the speed is going to be dependent upon your system. When we started to review this scanner last year, I bought this laptop new. It was a 13th Gen i7. It's got a decent graphics card in it. It's got plenty of RAM. But an i9, for example, will behave better. It'll go a bit faster. Other things, the surface finish of your parts, the number of markers in view, these are all going to have an impact. The power settings of your system and the utilization of the graphics card, all this information is going to affect the speed at which you're capturing. I'm going to go ahead and increase exposure a bit. See if I can't get a bit more off the backside. One thing I've noticed with either laser mode and the full field mode is the preview looks so much better in full field mode. And part of that is because we don't get as many of these reflections happening. Part of the reflections come from ambient light, comes from the surface finish of the part, the intensity of the laser lines. These all have an impact on what we're seeing. Now, as I understood it, Revoscan was working on a variation of the software that filtered out a lot of those points just for the graphics display because it can be very hard to see what's going on. The version that I'm using right now doesn't appear to have it. It's version 5.5.1. It was a public release version, but it still seems to have some of the artifacts floating above. They get filtered out pretty easily. The only real downside is that it makes it hard to see the part. I don't notice this if I've got a scan spray prepped part. I don't have the reflections and the noise like I do with a shiny metal part, so it's definitely something to do with the surface texture and surface finish. Let's just see if we can capture a bit more over here. I want to get as accurate as possible inside of the fork clamp area. That's really all I care about. And the laser lines, the cross or parallel lines, will do much better at that than full field mode will. But it's still a challenge because the size of the bore relative to the depth cameras, it just makes it so that it's really hard for both of them to see inside at the same time. So you have to kind of do this twist Just try to capture it. All right, let's take a look, see if we can dig through some of this. All right, so you can see the front is pretty rough, inside of there is pretty rough. So I need to capture more on the front. Yeah. So, see if we can get a bit lower since we've got some marker dots there. As soon as you don't have at least 4 or 5 marker dots visible, then it really starts to lock up. It needs to have those points, which is part of the reason I put the dots on the side here. All right, we're going to call that good. It's a bit of a mess, but we will go through and process it. Let's go ahead and do a new scan. And once again, we'll capture a new global marker file. And make sure that we get the front. All right. All right, just like before, we just have to go back and forth until everything is green. It's much easier to capture a few more scans now than it is to find out that you don't have enough and you got to come back and do it again. It's always a good idea too to have your part elevated off the bottom, or use the option to remove a flat plane. It's also helpful if the desktop or the table is black, because then it's not going to get picked up. So I'm going to work back and forth until the top is mostly green, and then I'm going to start to work around the sides. And the reason I say the top is mostly green is because with all the other captures, once we start tilting, we're still pulling in more information off the top. So spending that extra time on the top after that is not really worth it. We're just going to go back and forth. Hopefully we've got enough marker dots here. If you're only doing 2 scans, you want to make sure that you have enough overlap between the two so that you can align them. And the edge of the scans is always going to be noisy, and we're going to have to trim it away. So we have to make sure that there's at least 1 or 2 areas, which generally on this is going to be the front and the back, that have enough overlap so that way when we do go ahead and trim the bottom and trim the top, we don't have to worry about completely missing anything. So I don't have to get everything in this scan, but it is helpful. And if the part could be propped up vertically, which it could, or hung from something in a stable way, it would be easier for me to scan the front, the sides, and the back all at the same time. And with a part like this that doesn't have very many unique features on top, this is where full field mode kind of falls and it has trouble, where the global marker alignment for laser mode, or even full field mode using global marker alignment, really does show the benefits of that, because we don't have to be so careful about moving around too fast and jumping frames, but we do still need to try to get perpendicular to the part, which is quite a bit more difficult when we're dealing with using markers for alignment. And if we need to pull anything from like a mesh section sketch, we can do that using the a partial scan. It doesn't need to be a complete scan. So we don't have to worry about getting everything perfectly scanned. If we've got at least 30 to 45% of the fork clamp area, we can apply a circle to it and check the tolerance and see how close we are. All right, let's go repeat this over here. All right. Let's take a look. Looks pretty good. Yeah, I think that's good. All right, so now we've got a couple of scans. We've got a full field and we've got the cross-line laser. So now we can go ahead and hop back into my desktop. We can process these and we can just make sure that we've got everything we need. All right, so now that we're back at my desktop computer, we need to take a look at what appears to be just a mess of noise. But underneath that noise, we can see that we've got a scan. Now, again, I mentioned that versions of Revoscan change and update, and this is a sort of a known problem that I believe newer versions of Revoscan will take care of. But essentially, when we're dealing with a laser scan, and we especially have a shiny part, we end up getting a lot of these reflections floating in space. That stuff gets cleaned up automatically, so we're not too worried about it. It just really messes with the preview on the screen. You can kind of see here that the preview is just a bit messy. Now, one thing I did mention when we were scanning is that areas that are bright green are going to have good scan data that we can use to reverse engineer a part or get information off of. When the areas are not bright green, when they're sort of a lighter green or a pink or a red, then the scan data is actually pretty bumpy and noisy. And that's why we have to spend a little bit of extra time. So these top faces are going to be pretty good. These side faces are going to be pretty bad. So we're going to go back through a couple of the scans and see which models are going to have the best data. That one there was done with cross lines. This one here was done with full field. There's a bit of noise on top of it, but the scan itself looks like it might be okay. There's a couple of marker dot spots, that's okay. So what I'm going to do is I'm going to rename this. I'm going to call this full field bottom. And then we'll take a look at this one here. All right, so this one's a little messy. Again, the highly reflective parts. I strongly suggest scan spray on nearly everything. It just makes the job so much easier. It's not required, but it does certainly help. So I'm going to call this one full field top. And then we've got scan 1 here. One nice thing when we're looking at the raw data, when we're rendering or seeing the raw data on the screen, it will tell you in this bottom left what was used. So you can see here, high accuracy, global marker, metallic shiny object, cross line. So we're on laser mode. And if we zoom in, you can see that we've got the top, missing some data on the outside here. but we do have a scan that we can use if needed. I'm going to go back to scan 4 and 5. So this again was cross-line, and we use global marker. So this is cross-line bottom, and then this other one would have been cross-line top. So we'll rename that as well. Renaming these just helps when we get to go back to it. All right, so now that we're at this stage, let's go ahead and talk about the processing steps. There is, of course, a one-click option. I never use that. I always go to do this manually, and there are a couple of reasons. So first, we need to identify what this quality slider is and the point distance. So when we're talking about point distances, if we zoom way in, what we actually see are the captured points. And it's going to be a bit messy, but hopefully you can see some of these points on the screen. Now, if we zoom in, let's see if we can get an area where it's not so dense. Let's see. Now, basically what we have is we've got captured points, and these points come through based on the angle of the scanner and the frames that are being captured. Now, remember, with laser scanning, it's only picking up data where the laser lines are. In full field, it's bringing the entire frame in, so the table, anything around. But with the laser lines, we're only picking up where the laser itself is. But with that, we still end up with points in some cases that are closer together than others. So the point distance is going to be a way for us to take the average distance and make a fused point cloud. So we scan this at 0.3 millimeters, and setting the point distance higher than that is basically going to take all those points, and anything that's underneath that value, it'll merge them together. The quality slider is actually the really important one here. Now, the point distance is important, but the quality slider is going to have a direct impact on the amount of scan data we get. And I'll show you what I mean here. So I'm going to process this with quality set to 1. Now, this is probably going to take a little bit of time because it has to go through everything in the scene, all the floating points. But essentially what quality is looking at is the deviation in the height or the angle of the points. So when you have a scan that was done with laser mode that is bright green, we've captured a lot of points in that area, and we've gotten pretty much an average, a good sort of base level. When we've got areas that maybe the scanner wasn't perpendicular to, or there's still a lighter green or even a pink or a red, those areas, and we can kind of see them on the side of the clamp here, those areas are going to have a lot more height variations, meaning that the points themselves are going to be above or below the actual surface. And this is why it's important that we spend a lot of time scanning and capturing the data that we're interested in. And if we've got extraneous data, the points floating above the scan or stuff on the table, that can all be cut and filtered out pretty easily, so we don't really need to worry about it. So, but in this case, when we have the quality set to 1, which the default, depending on your install, I think it's between 0.7 and 1.0. Basically what this means is we're probably going to get rid of everything on the side of this clamp, and we're only going to be left with the top. This means the tabletop is going to be gone, all the floating points are going to be gone, and any of that extra data that is around the outside. Basically anything that wasn't bright green in our preview window is going to be filtered out. Now that's not universally true, but with my experience, that's basically how this quality slider works. So setting it all the way to the right to 1.0 is going to get rid of pretty much everything that wasn't a high quality result. Now you can see here we've got the top, we can see where the marker dots were, we've got the front here, you can see where those marker dots were, and again, for whatever reason, Revoscan still treats those tiny marker dots as the large ones. So when you're processing, you end up with them. You got to be careful not to get them too close to a corner. But you can see that we lost a lot of scan data underneath here. Scan data that might be helpful to us. So if we want to try to capture more and maybe use tools like Smooth and Simplify, we can bring the slider down, and I'm going to go halfway to 0.5, and I'm going to reprocess this. So when we reprocess a raw point cloud, it's going to delete what we did here with the fused points, and it'll basically start over from the raw data, and it'll recapture it. So this time I'm not going to talk through the process. I'm going to pause it, and then we'll hop back in once it's processed. So now you can see we've got a little bit more of the clamp. Obviously, there's more sort of trash on the table here, but this is able to bring in more data. You will note that the corners, which these are, sort of especially shiny areas, they are going to have a bit more noise on them now. So again, these are very important topics that we need to think about, but these settings are going to filter out a lot of information. So some of the castings that were sticking down on the bottom, those are gone. It kept a little piece of that clear cap that I had sitting there. But for the most part, we were able to bring back or retain some of that. So I'm going to go to the crossline bottom, going to go to Fusion. We'll set the settings the same, 0.5 for the point distance, and we'll set the quality at 0.5 and apply it. When we're talking about going from raw scan data to a fused point cloud to a mesh, we always want to think about the points and the sort of the accuracy that we're dealing with. There is going to be some associated noise in the scan, especially if you're dealing with shiny parts or black parts or shiny black parts in the worst case scenario. Then we are going to have to deal with these variations in the scan. Now, the good news is that we can filter some of this out using Fusion, using smoothing and simplification at the point level, which generally I would recommend against doing. I would say that you should do the simplification at the mesh level to better retain some things like the corners and edges. I find that if you simplify too much at the point level, you end up getting a pretty bad representation at the mesh level. It's not universally true. You can always take steps back, go back to the raw data, back to the fused and remesh, or back to the mesh and reprocess. And that's something that's important to play around with on your specific models. But in this case, I think leaving the point distance at 0.5, which is a larger distance than what we had our scanner set to, this is going to give us a lower point count, which means that when we transition to creating a mesh, we'll get a smoother overall mesh. If we've got a more dense point, so if we set this to say 0.1 or something smaller, depending on what we're scanning, then we end up running the risk of having a really noisy point cloud. And then we have a really noisy mesh. And then we have to really deal with some of those process settings. So you can see here that the noise sort of went away. Again, when we have marker dots that are close to edges, these present problems for us because the software is still treating those tiny dots as large ones. But we do have better overall results here. So this looks pretty good. And I think it'll give us everything we need. Once again, you can see the noise here. Some of this would get filtered out if we were to set the quality higher. The next step is to go to isolation detection. 15% is the default, and generally that will get rid of some noise. And then we need to do overlap detection. And again, this is looking at distances, so this will take care of some of these sort of straggling pieces on the corners. And then we need to do some manual cleanup. So for example, I need to get rid of this, obviously. And once that's gone, we're going to hit delete and get rid of most of this stuff. And one thing that we also need to do is we need to clean up some of these edges. And the reason for that is because if we start to process this and we take in these sort of jagged edges, what we're going to end up getting is a poor quality mesh at the end. So I want to make sure that I clean up any points around the edge because these generally are going to have more noise. They're not going to be as clean as, say something up in this area. So find those spots where you've got something that looks like it's out of place. Delete that. This section here probably is not great. You can see right there by the hole. I'm just going to go ahead and cut that out. Hopefully we got it clean from the top side scan. Remember, we're looking at the bottom now. Again, you can see that marker dot is going to be problematic. I don't actually need it for what we're doing because we're making a new clamp. So if that's not in the same location, it doesn't really matter to me. But we want to make sure that we clean all this up. Let's get rid of that. All right. So I don't love that marker dot's on the corner, but I'm going to deal with it. The inside area here is pretty noisy. Again, part of that is because of our settings. If the Fusion setting was set to 1.0, all of this would just basically disappear. It wouldn't have even counted it. But I ended up keeping it in there just to have a little bit more data, even though it's noisy. may come to regret that later, but for right now, we're going to leave it in. We can always cut it out at this stage. Let's go ahead and get this piece. So for example, if we know that this is, really bad quality scan, it's very bumpy, you want to make sure you're not selecting both sides so you can see it selected all the way through. So we're going to go to this option here, which will prevent us from selecting through. And we'll basically just grab this whole section here. Now, if we rotate this around, still grabbing the other side. Let's go ahead and clear that. So this is actually, that's the setting I wanted there. And now we'll go through and cut it. And we'll do it one more time. All right, so that's a little bit better. It removes some of those high spots. And we also want to cut some of this. Again, wherever we have the sort of bumpy nature on those corners, we can always come back and use tools to fill in small holes. But we want to make sure that where our scans are going to overlap, we don't have any problems. This is potentially going to be a problem here, so I'm going to just cut it a little bit. All right, so now that we've got this, I'm going to go back to the top one, go back to isolation detection, go back to overlap detection, and then we'll manually remove stuff. So once again, because we have it spaced above the work table, it's really easy to remove this. I do want to turn back on the select through. That way it'll let me get it all. And we got to get this piece here. So this was a top of basically a clear aerosol can. And I set it on. And then this piece over here. So now that we've cleaned that up, we'll do overlap detection again just to see if anything comes through. And then make sure that we clean up any edges that could potentially be a problem. So once again, you probably need to rotate this around. If you do have trouble seeing what's going on, you can change the display. I tend to leave this just kind of as the default. I know it's really hard to see from the backside, but generally I don't need to mess with it too much. But you can always go up to your display options and you can toggle things like the color and the way things are displayed. It works a bit better at the mesh level than at the point level, but you can still sort of tweak the UI and tweak the colors a bit. All right. All right, I'm going to rotate this a bit more. So there's a small step that happens at the bottom of this. And I'm going to hope that it's all captured from the other scan. So I want to get rid of some of that. I don't want it to be obscuring it. All right. Still doesn't look great right there. So I'm going to cut that part out. This is why it helps to have multiple scans, just in case you have problems. I'm not happy with sort of these edges here. Again, if I was going to be using this to reverse engineer, I would probably do 4 different scans, and I would use scan prep spray just to make sure that things like these corners and the shiny top don't produce a bunch of problems. At this stage, what I'm going to do is merge, and because I've only processed the 2 scans, these are the only 2 available. I'm going to try to allow it to do it with features. Generally, this doesn't work. You can see it's actually upside down. So this means that we need to do a manual alignment. So I'll have to pick 2. And usually what I do is I put them in the same orientation. That way I can select those points. So we're going to put that like this. We'll zoom in. We'll do 1 point over here, 2 and 3. And then on this one, you're going to pick the same areas. And it's going to basically, it's going to look in those areas. The closer you can get the points, the better off you're going to be. All right, so you can see it looks pretty good. Maybe some noise down here. But at this stage, we're going to go ahead and generate the model. So what this is going to give us is it's going to give us a merge point. So if we go back to, say, overlap detection, we now have a set that is merged. So we want to run overlap detection because this is going to leave a bunch of points on top. We also may want to check out isolation just to make sure there's nothing. And if you want to do any smoothing at this stage, you can. It might help with some of these corners. So I do recommend that the strength value be lower and the times be higher. This basically will limit the amount of distance the points can move, and it'll just run through it 29 times. So we'll apply. And you can see that looks worse, right? So what we're going to do is undo that. We'll take a step back. Maybe take the strength all the way down, the times all the way up. We'll try it. And not too bad, but it's still not great. I think the original was a little bit better. And what you can do is you can try to put the strength higher and the times lower and see if this gives you a better result. In general, it usually doesn't, but we do have the ability to undo. So playing around with it is certainly helpful. You can see now it basically softened everything up. It went a little too much, so I'm going to undo. I'm going to undo twice. And I'm going to put the times lower, say apply. What I'm looking is to try to clean up those edges. So I'm not happy with the way that's working because it's basically taking it too far away from the original cast part and it's making it just too rounded. So I'm going to leave it like this. I'm not going to do any simplification. I'm going to simply move on to the mesh stage. Now, when we go to the mesh stage, the grid size is important because this is going to be the distance or the size of the triangles. And we need to think about how far the points are away. We did our point fusion with 0.5 millimeters. So if I drag this down to, say, 0.51 and apply, this is going to use those points where we had everything placed that were approximately 0.5 millimeters away. If we happen to make this value much smaller than our point distance, things start to get pretty interesting in the results. Now, you will notice that we can see where those marker dots were. And again, it treats those small ones as these larger marker dots for whatever reason, but we can see where they are on the surface of our part. And this is one reason why I kind of prefer doing fusion. I didn't do any automatic cleaning and filling. At this stage, we could. So what we could do is come in, we want to turn off the select through, and let's just say lasso these, delete them, and then we could fill the holes. So we're going to use a plane option because the top of this part is actually flat, it's planar. So a plane option is going to give us a nice sort of clean area there. So what we could do is if we really cared about all these marker dots is we could do some cleanup. If the marker dot happens to be on a corner, well, we're just kind of out of luck. We just need to not place them near a corner. And if it happens to be on a curved surface, let's say down here, then what we could do, and I'll try to do this one here. What we could do is we could use the curved option to try to fill that hole. So I'm going to delete that. We're going to say methods, curved. I'm going to select this and apply it, and then fill that hole back in. So again, we could spend a little bit of time if we were really concerned about these. This one here being on a curved surface in one direction plus on this edge, it's not going to work out well. But again, I don't really need it, so I'm not too concerned about it. But that's what we would do if we wanted to go through and clean up all those points. At this stage, if we wanted to do any smoothing or simplification, we can. Again, we need to think about the times and the strength. These are going to determine how far the triangles can move. And once again, it's a good idea to play around with using undo. Letting it go more times with a lower strength will allow it to do more gradual refinement, but you can see what we're doing is we're actually losing resolution in these edges. And it seems to me that leaving this more in its original state is probably going to be better. You could try a mesh simplification, and it's a good idea to go to your model display and show a wireframe overlay for this. So if we zoom way in, we can see this is what our mesh looks like. If we do a mesh simplification, In areas where the angle between the triangles is relatively low, it's going to be able to put a larger, sort of a larger patch here. And you will notice that areas where we deleted those markers and did a larger sort of a patch, a fill hole there, looks a bit better. We will be able to zoom in to, say, these corners and note that the corners still have a higher resolution there. So what this allows us to do is reduce the number of polygons. So we have 305,000. This is something that Fusion or other mesh programs are going to work much better with. So now that we have this, I'm going to export the mesh, just the mesh model. So I'm going to call this GPZ triple clamp final. And the last thing that we need to do before we go into CAD with this is we actually need to align it. If we just bring this straight into Fusion, it's not going to be aligned. And we've talked recently about how to do that, but probably a better option is for us to use something like QuickSurface Lite. And that's exactly what I'm going to do. I'm going to bring this into QuickSurface. I'm going to generate some primitives and I'm going to align it. Now, remember, for our specific video, we don't actually need the part itself, but we just need the measurements off of it. So you could do this in QuickSurface. I opened up QuickSurface Pro, but it's going to work the same in QuickSurface Lite. But basically what we want to do is we're going to zoom in and we're going to start by extracting some primitives. So inside of this cylindrical area, I'm just going to try to select as much as I can. Let's select some over here. And I'm going to let it apply a cylinder. So I'm going to create and stay. I'm going to do the same thing over here. Kind of select these inside areas. You can see it's very noisy on one side, but as long as I have enough information where it can, let's maybe increase this a little bit, where it can put a cylinder in that location, create and stay. I'll do the same thing in the center here, create a cylinder, and we'll create and stay. And I also want to create a plane on top. Now we can turn the analysis on and we can see all the marker dots. We can kind of figure out if the plane is going to be close enough. We can see here the red areas are 0.15 millimeters. The blue areas are minus 0.15. The green, which is going to be these areas here, those are right there, right about 0. So we've got some red areas here. And what this means is what we can do is we can try again. So basically we're going to clear the selection. I'm going to pull the slider down to bring in less area, create a plane, and see if we can get closer to that, more of it being in that nominal area. So we can see here, if we move this around, it's a little bit red on this side, a little bit red on this side. Keep in mind with this triple clamp, it was originally a cast part that was machined. I have since machined certain features off and cleaned and sort of polished and sanded it. So the top surface is not going to be machined flat anymore. And we've got the marker dot. So this is not unexpected. So now that we've got that plane, I'm going to go ahead and say create. And then we can do an alignment. We're going to do align by coordinate system. My primary feature that I want to pick is going to be this cylinder here. So this is going to be cylinder 3. And that's going to give me the XYZ location. If I need to flip this, I can. But right now, I want to set it so that Z is up. Let's see, we want Z to be up. And then we need to drive the X orientation. So the second thing I'm going to do is pick the top plane. That'll move everything up. And then if I need to pick a third feature to align the coordinate system, I can. Right now, it's going to be okay. I don't really need to know where the cylinders are. But when we apply this, we do want to apply it to all features, which means that the cylinders and everything are going to move. We can apply it, and then we can close this. Now, with QuickSurface Pro or QuickSurface Lite, we have the ability to export the mesh, or we can export the solid bodies, so the scan data, or we can export what we created, those primitives. Now, based on our design needs, I could just export the primitives, but I'm going to do the scan data and bring it into Fusion just in case. So we're going to do GPZ triple clamp final, and I'm going to call this one aligned. So this is an extra step. It helps because what this allows us to do is it allows us to put it at a coordinate system that is known once we bring it into Fusion. The next step of our process is going to be to hop into Fusion and model the triple clamp. Now, obviously, I've already modeled this triple clamp because I've ordered it and I have it on hand, but this is basically what we're going to be modeling, and we're going to bring the mesh in as a reference. The first thing that we want to do in Fusion is have a new file, and if we are using a mesh, we're going to insert the mesh. So I'm going to go to find it on my computer. This is GPZ triple clamp final aligned. And because we went through the process in QuickSurface, you can see here that it is aligned. The XYZ is on top and Z is pointing up. Now it is backwards. I do want to rotate it, but I don't want to rotate it because the pivot point is not in the correct orientation. What we could do is simply say, okay, we've placed it. And then now if we want, we can go into bodies. We can use move copy. We want to reset the pivot point to be at the origin. And then we can simply rotate it about Z 180 degrees. That's going to keep XYZ in the same location. Now when we look at it from the top, X is pointing to the right, Y is pointing forward, and Z is pointing up. So at this stage, again, the main thing that we really need is we need to be able to know where these points are. Now, I will say that I have measured it and I know what numbers I'm going to use. It's 205 between the two fork holes. They're 43 millimeters, and this is a 34.25 offset. We are going to have some sort of variation from that based on the quality of the mesh. Like, we know that some of the mesh area it's got these high and low points. We've got some holes that we're going to deal with. And the fact that this isn't currently clamped, this does get deformed a bit. So it's not going to be a true circle anymore, just because this was from 1989. So it's been around quite a while, been on several different bikes. So what we're going to do is we're going to start a mesh section sketch of this mesh body. We're going to select the top plane, and then we're going to pull it down. And we want to get a good reference for all three of these holes. And once we have that good reference, then we can go to whatever sketch is created, right click and edit the sketch. I'm going to hide the mesh for now so we can kind of see what we're working on. And from here, we're going to use fit curves to mesh section. We're going to use circle. We're going to select the mesh section. And again, notice you can see how it's a little bit outside here and it's a little bit outside here, meaning that it's not perfectly aligned. And again, part of this is because the way that the clamps are designed, it's not clamped on anything right now, so it's going to be deformed slightly. So we need to think about this deviation. You can see the max curve deviation is actually 3.7 millimeters. If I were to select this point here, this is going to give me a difference because now it's just trying to fit that smaller section, and the max curve deviation is going to be different. So these are all things that we need to kind of worry about when we're using this process. Once again, tools like QuickSurface are going to be a bit better and more accurate, but we also do have the ability to get pretty close with this. So once I've placed those three, I'm going to use my line tool and go from one to the other, hit escape, and then we're going to use our dimension tool. We're going to go from here to here. And it looks like 34.63 is that distance. And then if we want the distance between these two, you can see it's 204.882. So from my measurements, I know that this is actually 205 millimeters. Knowing that we're a little bit off because the clamp is deformed because it's not in its sort of final state to clamp on the forks, 204.882, roughly a difference of 0.1 millimeters. That's well within tolerance of anything that we need. Basically, in inches, that's 0.004, roughly 0.005 inches. So that, that's perfectly fine. This distance from front to rear is coming out at 34.636. Now, I mentioned previously that the way that the forks and everything sort of bind on the bike, and the stem is one that I made years ago, there is actually a little bit of deviation. Now, 34 0.6 is a bit too far away from the measured number that I have, I'm going to be using 34.25 because that's what I measured off of the top triple clamp. Now, part of that deviation is going to come from the fact that these holes are shifted a little bit. So you can see the center of this hole is actually a little bit higher than the bottom portion here. So we're going off of the center distance. Now, if I hit escape on my dimension tool and I try to drag this down a little bit, I'm going to hold down control so that I'm not actually snapping to anything. I want to get it so that the circle is roughly centered. And this one over here, I'm going to do the same thing. And then I'm going to go ahead, actually let's delete that. Go over here and bring this down. And then measure it again. So you can see now we're 34.33. So again, these are problems that we run into when we're using meshes. And we have to really fall back and rely on our measured dimensions for critical features. The scan that we have here can certainly be used as a reference for designing the geometry, but pulling critical dimensions off of it as the only means to designing a part can be a problem. So measuring the diameter of the holes, measuring the distance between the forks as best you can with the tools you have available, and measuring the offset front to rear, which is the more difficult one to do. But if this is on the bike and you can actually get a reference from the back side of the fork or the front side of the fork, that can help. Basically what you can do is you can measure from the back side of the fork, knowing their diameters, and then measure to either the back side of this or the front side of this, knowing its diameter, and then you can do a little bit of math and figure out those locations. So with all that said, all of that process was solely there so that we would have the triple clamp scan as a reference to design our part, and we could use it to confirm, validate, or look into the measurements between these points. Knowing that they're pretty close and knowing that in most cases, these parts are going to be designed with nice round numbers, so 34.25 millimeter. It might actually even be closer to 34 in reality, and 205 millimeters. These seem like the right numbers to go with. I do want to say that with this process, it is important that we also 3D print and do some testing. So you could very easily print a piece that had the two cylinders 205 millimeters apart, and then you could put a slot in this location, and then you could have some marks on the side and sort of figure out where the stem is located to help you measure those features. So designing your own tool can be a helpful way to get that as well. And then you can go back to the CAD and figure out, where those features are located. For our purposes, what I'm going to do at this stage is I'm going to right click and I'm going to make the mesh unselectable. So every time I move my mouse over it, it doesn't highlight and drag the process down. And then this file with the mesh in it is going to be in the description of the video for you. Okay, so if you're still with me at this point, the next step in our process is to start designing our triple clamp. What I'm going to do for right now is I'm going to hide the mesh and I'm going to use just dimensions. So I'm going to start a new sketch on the top plane. I'm going to start with my stem at the origin, and the stem is going to be 24 millimeters. These numbers could come from measuring the actual parts. And then I'm going to do a 42 millimeter circle. This is going to be the outside or the extent where it clamps. And you can see, again, these dimensions are going to be coming from the clamp and from measurements that I've taken. So if you're designing your own part, you need to think about the amount of material you need if you're trying to replicate another triple clamp, if you're trying to replicate something else. Next, what I'm going to do is create some construction lines. I don't need to see the origin anymore, but I'm going to create a construction line up. Then I'm going to create one horizontally. These will be converted to construction by either clicking in the sketch palette over here or hitting X on the keyboard. So either one will work. Then we want to take this endpoint and this line and make a midpoint relationship. Then we're going to do a dimension, D on the keyboard. It's going to be 34.25, that value that we're going to use. And then this is going to be our 205 millimeters. So what we're doing now is we're laying out the basic shape of the triple clamp in a top-down sketch. So we'll use constraints whenever possible. We'll set the two centers equal. We'll set the two outsides equal. Actually, this one and this one will be equal, and the inside will be equal. And then we'll use our dimension tool again. So we know that it's got a 43 millimeter fork. And then the outside, I'm going to use 55. And again, if you want to bring back the triple clamp at any point in time, you can take a look at it and see how close we are. And then we need to draw some lines. So what I would say is that we obviously want tangency coming off of the clamp here. And we can use a mirror relationship. I'm going to just bring a line here. We'll say OK. So this we want to have tangency here. This we want to have tangency here. And then we're going to dimension this. So the dimension that we're going to use here is 10 degrees, simply based off of the shape of the original triple clamp. I'm trying to keep it looking as close as possible to the original in terms of that top-down shape. And then we can use more constraints like parallel to make sure the front and the back are parallel, vertical constraint with the origin and this point. And then we can mirror this line and this line over to the other side using our vertical reference here. So this gives us a closed profile that we can extrude to build out the base shape of our triple clamp. Now, if we were going to make a very simple triple clamp that was essentially flat, and we wouldn't have to do too much more work. So now we can finish our sketch, and we're going to extrude. So the overall height that we're going to extrude, because we are creating a triple clamp that is going to allow us to drop the forks down and raise the front end of the bike up by an inch, we need to make the overall height of this, the distance or the height for the portion that clamps onto the stem, and then the distance or the height that clamps onto the forks, and those need to be offset by 24 millimeters or roughly an inch. So the height that we're going to use is 24 millimeters, plus I want an additional 19 millimeters, which is going to be the thickness or the height at the top. So now we've got a super tall triple clamp. The original one is below it. I did that intentionally because I wanted to leave this one down here invisible. And we need to decide how to break this up. So what we're going to do is create a sketch on our front plane. And this sketch is going to represent the geometry or the solid body that we want to keep. So we need some reference lines, and this can be done a couple of different ways. But I'm going to create a horizontal reference line here. I'm going to create another horizontal reference line here. And then I'm going to create some vertical lines that go to the midpoints. And this is going to help me keep them aligned. So basically, this is going to be vertical. This one will be vertical. We'll hit escape. That'll be construction, and that'll be construction. So this one here is going to be basically the position that goes on the top of our frame. So we need to add a dimension, so D on the keyboard. This is going to be our 24 millimeter drop, or raising our front end up 24 millimeters. The width of this, it really varies. You can look at the original triple clamp and decide how much space you need. But basically what I look at is the size of the frame, where the upper bearing is going to be. There's generally going to be a large cup over it, and we'll have to just make sure that we have enough clearance around the frame. So for me, this value is going to be 55 millimeters. This top edge here, we want to snap to the top of the triple clamp, the extrude here. So I'm going to say coincident with this point. Now that'll bring this point and project it into my sketch, and this one can still kind of float back and forth. So another thing that we may want to do is project another reference point. So this can be done with P on the keyboard or project include. And then we may want to give it a dimension relative to other geometry. So for example, 10 millimeters wide. Because we have our midpoint relationship here, this means that it's going to be symmetric, and the 10 on this side is going to be the 10 on this side as well. So this is a little bit wider than the 55, but this gives us a good place to sort of determine where these points are. Now, if you decided, let's go ahead and delete this, and decided that you wanted it to be narrower up top, then we could simply drag it inward and we could place a 10 millimeter dimension here. Now, this step of the process, when you're figuring out what the geometry looks like, this can be extremely handy to have a 3D printer available, because you can create the geometry, make sure that everything mechanically is going to be sound, print it out, see how it looks on the bike in reality, see how it fits, and see if you need to make any adjustments. This upper portion, the main thing is it needs to be large enough for the hole that goes through. So you can see the hole is kind of right here. And that is going to be a problem if this flat section is shorter than the hole. All right, so these are kinds of the design decisions that we need to think about. So what I'm going to do is I'm actually going to select the hole, actually the upper edge of the hole, project it with P on the keyboard, and I'm going to use the edge of the hole as my dimension reference. So I'm going to grab it there, go to this one, and then we'll just use that same 10 millimeter dimension. So basically what this is saying now is we have the hole size that's going through, and we want the flat part on the top to be at least 10 millimeters outside of that before it starts to taper away. So using those as our references, we've now got a good understanding of where the bottom is going to be and where the top is going to be. The other thing that we need to do is we are going to basically do the same thing with project include. Again, P on the keyboard. I'm going to grab the bottom edge of both of these, even though we can mirror from one side to the other. And I'm going to do the same thing. So I'm going to go from this edge, and I'm going to come out, and I'm going to make this a distance of 10 millimeters. I'm just using this as a rough number. If we have to come back and change it, that's fine. But then we can go up. I'm going to hit 24 here. And then we can start to come over and then come up to this point. Now on the bottom side, we're going to go from here, maybe come over another 10 millimeters, and then come up to this point. So the last thing that we really need to figure out is where this is going to end in space. Do we want these to try to be parallel, because this thickness, 24, is different than this thickness? Or do we want to just say maybe these 2 points are vertical in relation to each other? That's just something that is going to be an aesthetic thing, and it will have an impact on maybe manufacturability. But for the most part, having these parallel is not going to be as strong as having this one taper out a bit wider, because the heights are different. So that's what I'm kind of going off of here. Then I want to mirror everything I did on this side. So this line, this one here, and this. And we'll use our vertical reference line and just mirror it to the other side. So now we've got a closed profile to work with. Once we have this closed profile, we're going to extrude it. It's going to have to be 2 directions. So we'll say 2 sides, because this one needs to come back a bit. And what we want to do is we want to use the operation called intersect. What this is going to allow us to do is take what we did from the top-down view and what we did from this front view, and it's going to keep only the overlapping geometry. So this allows me to keep the 3D complex shape that I have, and now I can continue to add detail to it. And if I ever want to go back and change, for example, the diameter of that first sketch, because our references for this back sketch here were based on projections from the diameter of this hole and projections from the diameter where the forks are, that means everything else should update properly. That's part of the reason why I like to use those as references. Now, I like to leave the fillets and rounding off bit until a little bit later in the design, simply because in a lot of cases we're going to add features, and having a fillet in the way can complicate things how they blend later. So we're going to carry on adding a section where we're going to clamp to the fork, for example, and we're going to do that by first starting with, actually let's go to sketch 2. We're going to go and create an offset plane. We're going to go from our right plane, but we want to snap to a point. So instead of distance, we're going to say to object and snap to this point. And again, the reason we're doing that is because this brings up a prismatic or parametric relationship. We're using the reference at the center of that hole. And if we happen to change the location, let's say we end up doing an upper and a lower triple clamp and we want to make them wider or narrower for whatever reason, then this point or this plane is going to float with it. So I'm going to go ahead and just make the plane a little bit bigger, but we're going to use this to not only create the geometry to add the sort of bolt or clamping portion, but we can also use it to split the clamp or do other things if we need to. So the way in which we clamp the fork together is going to be largely like the original, just a single bolt on the side. And that's perfectly fine for this design. If you want to make taller triple clamps or recess the bolts into the back or something like that, all that can be done. It's all personal preference. But for us, we're going to use this as a new sketch plane. We're going to go to Create, Project Include, and Intersect. And I want to grab the inside and the outside. This is going to give me the inside reference, which is important because we're going to make geometry to extrude. And if we just simply go to the outside reference and extrude, it's going to be floating out in space because the triple clamp tapers away. The next thing that we want to do is use our line tool and find the midpoint reference. So that's going to allow us to have a good center point location that we can use as a construction line. And then we can add geometry for the circles. So I'm going to add a 20 millimeter circle here, and I'll add another one. It's going to be 10.5. Now this bike uses a 10 millimeter bolt. It's going to be a 10.5 millimeter passing hole. And then when we add the actual threads later, Fusion will resize the portion where the threads are to the smaller appropriate tap size. So that way we can just have it oversized as our passing hole now. Let's go ahead and add a dimension here. And let's set this to 7 millimeters. So it doesn't go, the 20 millimeter doesn't go all the way to the inside of the fork, but it leaves enough room for the passing bolt to not interfere with this geometry. We certainly could bring it in tighter if we wanted to, but this is going to be fine. And then I'm going to create a horizontal line that is both tangent to the circle and perpendicular. So make sure that we do have that tangency. The lines should all turn black, meaning they're fully defined. And then now when we extrude this, we'll be able to grab those other profiles and extrude this without it leaving a gap or something on the backside. So let's go ahead and finish the sketch. We'll use extrude, hold down Control to select all the profiles we want. And we're going to do this 2 directions. So it's going to go, let's go to 22 millimeters there. We'll set this to 2 sides. And let's bring this out. 16 looks like about as far as we can go without this coming out. Now we could go further if we create a larger block and trim away the inside, but this is about the extent we can go with the direction that we went here. I'm going to join these together and we're going to say, okay, we're going to do a little bit of work and then we'll mirror this to the other side. Another thing that can be pretty handy is on the original clamp, this back face was tapered. Now, it doesn't really have to be, but it is a nice look that I want to follow. So the way I'm going to do that is by using Move Copy on the face. I'm going to reset my pivot point to be at the back edge there, and then just rotate this face. And it looks like about 20 degrees will probably get it. We'll say okay. And now you can see that has a very similar look to the original clamp. Now, it doesn't really come as far into the triple clamp. You can see that this one is a bit thicker, but again, it's fine. These are sort of design decisions that we need to make. The next thing that we want to do is mirror that to the other side. So sometimes with features like Move Copy, that can potentially be problematic when we try to mirror them as features. But let's go ahead and just try it. And if it doesn't work, then we'll have to use mirror faces. We'll say, okay, allowing it to adjust. And you can see here that it flipped it. So if we say identical and okay, you can see it's still flipping it because of that Move Copy feature. We've also got an optimized, and you can see there the optimized worked. So when you're using features like Move Copy on a face for geometry and you're trying to mirror that to the other side, you may need to play around with some of those calculation options to get it to work. If that didn't work for some reason, you can always go into use mirror faces and then just select the faces that you want to mirror, including the ID, and you'd have to rotate it around and get these. And then you could mirror those faces in the same way, and it would recreate the geometry. But in our case, using the optimized option allowed us to get the correct geometry. Now what we want to do is split the clamp area so we can actually clamp down, and then we can address doing some other finishing work. So I'm going to create a sketch on the top plane. We've got the center point location here. We can pull it from a sketch, or we can project, so P on the keyboard to project basically that inside diameter, which will give us a center location. Do that as well. And then we want to create a basically a 4 millimeter gap. So I'm going to do a straight line here, and then we can offset it. It's going to be 2 millimeters. And then we want to offset it the other direction, so minus 2 millimeters. Make the inside one construction, and then we'll just cap it off with a line here and with a line here. Another way that we can do this on the other side is we can draw a rectangle that's 4 millimeters wide and let's just say 75 long. And then we can use midpoint between this and the center point here, and that'll fully define it. So either way works fine. You could play around and make adjustments to these features. I'm going to go ahead and put a midpoint there. This one's underdefined for some reason, but we'll put midpoint there. And then we can define it the same way. So either option works fine, just depends on what you feel comfortable with. And then we're going to extrude both of these profiles. You will need to make multiple selections because of that projected entity there. We want to make sure that it goes through everything. So we're going to say symmetric and through all. And then objects to cut. Because it's going the sort of down direction, it does not like it. So you may need to use basically just some manual options. We could also go one direction because it is from the bottom plane as long as it doesn't leave a little remnant there, and we can allow it to cut all the way through. All right, so far it looks pretty good. We haven't saved yet, so it's probably a good time to make sure that we do save. Now that most of the geometry is done, we're still going to cut some holes through here, but I'm going to go ahead and add some fillets. So the size of the fillet is going to have some indication on manufacturability. So this part is going to require multiple directions to be machined. Now, if somebody is machining it from stock this way first, I want this fillet to be fairly large. So 20 millimeters will allow for a nice large tool to come in and go around this shape completely. And same thing from the top. So if we use a fillet on these vertical edges, I'm going to go ahead and set this one a bit larger at 25. And again, if somebody is machining it from this direction, which they'll have to do for the 3 holes and the bores and all that stuff, this is going to be pretty easy until they get to the clamp here. And this is going to require some finishing work with a smaller tool. So a lot of this could be done in a couple of 3-axis orientations, a multi-axis machine, or 3D surfacing. But making sure that at least the majority of it has a large fillet can be extremely helpful when we begin to talk about just basically overall manufacturability. Remember that this video is sponsored by PCBWay. They are the ones that machine the clamp for me, and we'll talk about them a little bit more when we get to the CNC portion. But for the most part, manufacturability is always a concern, and making some small or minor changes can sometimes make the price difference quite a bit more. So make sure that you have at least a firm understanding of the tool sizes. Like putting a 20 millimeter radius here means that the diameter of the tool can be pretty large to cut this geometry. The next thing that we want to account for is on the bottom face here, we're going to start a new sketch and create a circle that's 27 millimeters. There's a small recess that happens in the bottom of this triple clamp that is just how it was OEM. It doesn't really have an impact on the way I have it on the bike now, but I'm going to retain it just to make sure. Maybe this front end goes on back on a GSXR one day. I just want the triple clamp to have that functionality, and it's been on the bike in this fashion for a while now. So minus 4 millimeters is how deep that little bore goes in, and we're going to go ahead and just make sure that we include it. The next thing that I want to do is I want to start to break some of these edges. Now, generally when we're machining a part, if we don't have any corner treatment, then it's going to get tumbled, which means that it'll just have a slightly broken edge, or maybe a deburr tool is run around it just so it's not sharp. If you want a specific feature, so for example, a 1mm chamfer, then we want to make sure to manually add that to the design so that way it can be included as a machined feature. So in this case, I want something more than just a broken edge, and I don't want to put a fillet on the corner because that will be very expensive to machine. So putting a chamfer would allow them to run a sort of a chamfer mill bit around the part to clean up that edge. I do need to be careful that it's not so close to this feature that it ends up causing a problem. So that's why I'm not using anything larger, just because of the size of this clamping area. So we'll go ahead and say OK to that 1mm chamfer. Next, I want to start to add some fillets. So the front and the rear of the clamping area, I want to put not a huge fillet, not the 20 or 25mm radius that we used, but something large enough that a tool, so example, machining it from the top, if they end up using something like a 20 or a 24mm large tool to cut the majority of the clamp, you only have to come back with like a 12 or 14mm to be able to get into that corner properly and clean it out. So I want it to be big enough that it's easy to machine, but not so big that it starts to go over the edge of the hole and cause problems when we start to clamp this thing down. And I want to go back and add a small fillet. So let's maybe grab this edge and see what a 1mm looks like. And maybe between that, let's go ahead and remove this front edge. So we're going to add a 1mm fillet here and here. Now it looks like it's not liking this because of the distances here. Now, in some cases, when this happens, you can select cancel. We can go back before that 8mm, and we can try to add a 1mm here and see if it works. I'm going to hold down Control. And we're going to go ahead and do this over here as well. And sometimes it's the order of operations that causes the problem. And now if we do this one, it should blend okay. But you can see what ends up happening is it's not extending that fillet out. So in reality, it shouldn't look like that. We shouldn't have it just stop there. So what this means is we either need to use a smaller fillet, or potentially we need to readdress the size of this boss and make it a little bit smaller. So that way we have more room to blend these together. So I'm going to try a smaller fillet first. Now keep in mind that when we decrease these sizes, let's see if we can go back up to 1mm. When we decrease these sizes, this means that a smaller tool is going to have to be used to finish this geometry off. Now, in reality, I think that I would probably just reduce the size of this boss if I was going to do this again, because the first time around, the 1mm fillet actually fit just fine. So there is a potential problem with the geometry that it's not liking, but these are the issues that we oftentimes run into. I'm also going to try to add a fillet to the front and back edge just to make sure that they're not sharp. I'm not going to do anything to these edges because from a machining standpoint, that would be extremely difficult to manufacture. So I'm going to just go ahead and leave those edges sharp. They're not really a concern when handling the part because you're not going to stick your finger inside of that gap there. But for the most part, that looks pretty good. Now that we've got most of the clamp done, really the last thing for me to do is to remove some weight. And then we also want to think about any additional features or mounting holes. So I'm going to do a sketch from the top, select this top face. And I also want to select these two faces and hit P on the keyboard to project them. And then use my offset tool. So we're going to go 6mm inward. So it's going to be -6. And we're going to repeat that on this side here. So we'll say -6. And we'll repeat that here as well, -6. And then we want to add a circle that's centered here. And the circle, let's make it 34mm diameter. So this is going to give us basically these three areas that we can cut through the part. So we'll finish the sketch, extrude, and we'll pull them down and just simply say through all. So this is going to be a good way for us to remove some extra weight that's possibly not needed. The upper triple clamp on motorcycles takes a lot less of the load than the lower triple clamp does. Most of the load from the forks is going to be going into the lower portion of the frame, and the upper one is really to help there, to prevent some twisting, and it does take some load, but it's going to be quite a bit less than what the lower triple clamp is going to see. And that's why when you look at OEM clamps and you flip them over, the castings are generally pretty thin because they don't need a lot of material to perform what they need to. But now that we've removed that material, we do want to round the corners off. So I'm going to hit F for fillet, and I'm going to hit 8 millimeters, hold down Control, and then just go back and grab all the other ones. You could use a rule fillet, but honestly, there aren't that many edges for us to select, so I'm just going to do it manually in this case. But a rule fillet would allow you to select the feature, and it would be a quick way to do this. And for consistency's sake, I do want to add that 1 millimeter chamfer that we put everywhere. So go ahead and select the upper and lower portions of each of these holes. That looks pretty good. We'll say OK. And let's actually go back and edit that feature. I'm going to hold down Control, and I'm going to add this to these other areas as well, and this one here. All right, we'll say OK. And a couple more things that we need to deal with now. We want to add some additional mounting holes for other things like speedo or gauge or number plate, or potentially if we decide to add bar clamps, we could use these pockets. So I'm going to add some threaded holes on the front and back. I'm going to add some threaded holes underneath here. And we need to address the threads for actually clamping this thing on. So the first thing that we're going to do is go to our thread tool. We're going to select this hole. And this is going to have an M10 by 1.25. So we need to make sure that we select the appropriate one. Hold down Control. Remember, we don't need to worry about modeled threads. This is going to get CNC machined. So Fusion automatically is going to take care of the size of that hole. It's going to be sized appropriately for the class and fit of the thread designation you choose. When we're dealing with metric threads, there's only one class option for this size. If you're dealing with imperial threads, you may have some other options like 2A, 2B. But for right now, just note that it is going to resize the hole for us. And all we need to do on our detailed drawing is say it's an M10 by 1.25. Next, we want to add some threaded holes to the bottom. Again, I'm not exactly sure how the number plate's going to mount or how anything else is going to mount. So I want to just have a couple of options. So we're going to start a sketch on the bottom. And I want to add a point over here, and I'm going to add one over here as well. I'm going to make sure that these points are horizontal with each other, and then we're going to add some dimensions. So from this position here, we're going to go up 40 millimeters. And then horizontally, let's see where 17 millimeters puts us. And this one over here, I'm just going to click on the first dimension. And then we're going to use our hole tool. You can use H on the keyboard if you want. We'll do placement from sketch, select both points. This is going to be a tapped hole. The diameter we need to pick because it only has a sketch point. It doesn't know what size it is. So we're going to go down to 6 millimeter. And we're going to do, let's say, an M6 by 1, but we don't want it to go all the way through the part. So let's say we know the top is 19 millimeters. Making it a blind hole at 15 will prevent it from going all the way through. So we'll say OK. So that gives me 2 tapped holes down here. And next, I want to create some tapped holes on the front as well and the back. Again, in case I decide to put handlebars on, I can use these to build a clamp that fits in those pockets, or I can use it to mount some other thing like a gauge, a tack, or something if I need to. So we're going to create a sketch on the front. Going to rotate this around and project, just P on the keyboard, project those faces, and then I'll use a line. Basically what I want to do is I want to find the midpoint, and I'll do the same thing over here. Find the midpoint, we'll just go from one to the other. X for construction, and then let's put a hole on the middle of that, and a hole on the middle of that one. These are going to be, we'll just make them 6 millimeter holes, and we'll set them equal to each other. Now, the reason that I'm doing a hole here instead of doing a point like we did before is because the hole tool works great, but when we're dealing with going through multiple features, it tends to get a little tricky. So I'm going to hold down the left mouse button, select the profile, hold down Control, and then what we want to do is say two sides, through all in the one direction and through all in the other direction. And now that we've got the hole, we can go to our thread tool, and it automatically knows the size of the hole is 6 millimeters. So it can pick an M6 by 1. And if that's the size that we want to go with, which is the same as the one we used under here, we just say OK. And now all the holes have been resized appropriately. All right, let's go ahead and save this. And at this stage, it's a great idea to 3D print this. Make sure that it fits. Make sure everything in reality works how you want, that you didn't have any issues or errors. And this is pretty straightforward. Is basically if you've got a printer that's big enough to fit this, then you can print it with supports underneath. Because it's so hollow, there's really not much support that's needed to print this, but it doesn't need to be solid. Just use an infill amount that makes sense. That way you can have just a physical representation. So you can see that it doesn't fit as is, but if we rotate this, I'm going to go ahead and rotate it roughly 45. And this is a Bamboo P1S. So I also have a K1 Max that it fits on a bit easier, but it fits on a P1S just fine. And all we basically need to do is just enable support. I'm not going to go through this process because you're going to use whatever slicer you have, but just make sure that you turn on support. I like to use tree support and then slice it, and then we can get a 3D print. Now, I've printed this clamp twice. The first time I printed, I made the upper section 24 millimeters like I did the clamping section. Now, in reality, I ended up going a bit thinner for the machined part, making it 19. And that was just simply based on the stem and making everything work a bit easier on that side of things. So everything looks pretty good. We can see that the total time to print this would be 3 hours and 40 based on the material settings that I have, just a PLA silk material. Now, obviously, you could print it faster. You could use less infill and so on. But overall, this is a great step in the process to be able to double check yourself. And it fits on the bike. Everything works just fine. You can double check things like the clearance, moving the bars left to right, make sure that doesn't hit anything. That's a big factor. And make sure that it does actually raise the front end the amount that we want by making those measurements. So let's go ahead and close this out because I've already printed it. I don't need to save any of that. And the last step before we send this off for manufacture is actually to go through the process of creating a basic detailed drawing. Now, detailed drawings aren't required for every machined part, but if you do have any additional tolerance requirements or if you do have threaded holes, it is important that you do create a detailed drawing for that. Now, what I'm going to do is create a basic detailed drawing. I'm going to do from design. I'm going to use the automatic or the automated modeling or the automated detailed drawing. And I'm going to pick an A4 sheet size. First level, it's only a single part. It's not going to include the mesh, and we'll say OK. Now, if you haven't used automated drawings before, this is a way to automatically create a detailed drawing. It'll give you some options for the density of the dimensions. You may need to go back and add some of your own dimensions, but it simplifies the drawing process, or at least the beginning of the drawing process. It is not going to give you everything you need. It will, however, give you a lot. You can see that it made the size of the clamp way too small. It's still going through all the different dimension schemes. You can see that it's got multiple views here. So if we click on one of these other options, you can see that the views are just placed out in space. So we would need to sort of reposition these after. But the big thing that we want to focus on is the dimensions that we want, how many dimensions we want, and whether or not we need to pick a different dimension scheme. Now, in reality, I think that this is actually an easier part to just do manually. I'm going to say OK and allow it to create this, but I'm going to pull this up, pull this one up, pull this one over, and I'm going to double click on this base view, and I want to change the scale. Let's try 1:4 and maybe 1/2. There we go. All right, and again, the main thing that PCBWay is looking for is information about the holes. So under the dimensions dropdown, we've got some options for using auto dimensions. Under text, we've got some options for notes like hole and thread note. So if you select a thread and bring this out, it'll give you the information about that hole. So this one here, if we select that, you can see that there's 2 there. This one here, if we select that, there's 2 there. There's 2 there. And basically, these are the main notes that PCBWay would need. They need to understand the size of the threads that you're using. So we've got 2 M10 by 1.25s. We've got the 2 M6, and I'm going to go ahead and pull these out of the way. And I'm actually going to let's delete that, and delete that. Really, all I care about is that hole. And then we're going to do another dimension for this. And if I select it and right click, let's go ahead and actually go to dimensions, and let's do a diameter dimension here. So it gives me the 43. So once again, put as many dimensions as you feel comfortable with, but the main thing that is needed for manufacture is to understand the holes, the actual holes that are being produced. If you want to grab the larger hole here, it doesn't work because that wasn't created with the hole or thread tool. That hole was actually done just simply as a 10.5 millimeter hole. So that one is not really a concern. It's really only the threaded holes. But again, you could add any additional notes you want. And then from here, we would just export this as a PDF. Now, I actually have a detailed drawing that I sent to them, and I will show you that one. So again, it just has the basic information, M10 by 1.25, 43 millimeter diameter, the M6 holes, and I put 4 times this one instead of 2, and I've got the diameter here, and again, the thread notes. So really just some basic dimensions, overall width, overall height, and the hole notes. And that's all I sent in to get this thing manufactured. Now, the process of setting up a quote is pretty straightforward. We just need to head to the PCBWay website, say that you want to start a quote for CNC machining, the quantity, the material, and select Get Started. We're going to drag and drop the design. And once we have the design, we're going to pick the units, the material. 6061 for this is going to be fine. And then if we have any additional surface finish options that we want, so in this case, do a bead blast, so it gives it sort of that rough finish and an anodized color. Pick the color and submit. And then basically there are some notes, depending on the post-process. There may be a spot where they had to hang the part from for the electrode, for example. Generally, that ends up happening in like a threaded hole. And there's just a note that you may see that. So we've got the material. If there are any surface finish requirements, or if you have any information about the hole sizes, then you need to upload a technical drawing. And then, do we need tapped threads? Yes. Do we need inserts? No. Any additional tolerances? So if there are tighter tolerances required outside of just the general ISO standard that they use, then you will need to select that. It will increase the price, and you will need to put those requirements on a detailed drawing. So if you've got data measurements that you need, or a tighter tolerance for a certain area. For triple clamps in general, because the clamps spring out and spring open and have some adjustability, as long as the passing hole for the M10 screw is large enough, the clamp variations within the normal tolerances are going to be fine. Now, obviously, if you're doing something like a press fit bearing, that's a different story than a triple clamp that needs to slide over. The surface roughness, again, this, if you want to have a highly polished finished part, then you would need to change this. But because we got it set to do a sandblast and anodized, this actually isn't really going to matter too much. Doesn't need to be assembled. Standard finished appearance. If you want a higher finish, so again, for example, if you want them to do, make sure that there are
no potential surface issues. They'll also include photos before they ship the parts out, which is kind of nice. And then a standard inspection if you don't need an actual inspection report. So for example, if you do want them to inspect certain features, make sure they're within tolerance, then you will need to provide a detailed drawing that has those measurements with those tolerance values required, and then you will need to pay extra for that. If you want them to do a CMM machine or some sort of material certification, that will cost extra as well. Now, you can also add the product description, so you'll need to pick that it's a vehicle accessory, and then you can put any additional requests here. Now, what I've found with this process is PCBWay is a Chinese company, so there are some inherent delays that you may need to sort of deal with, but the triple clamp shipped to me was about $220 from them. I could not get it machined for under $1,000 at any other rapid place here in the United States. And that's a big enough difference that it just doesn't make sense to do it here. Now, the lead time for me was actually quite a bit longer than 6 to 8 business days, but partially because I did this during the Chinese New Year, so there was some delays there. I found that it was machined relatively quickly, and then the sort of quality assurance QC portion of it took probably about 8 days for me. But again, it was during Chinese New Year, so they did advertise that there were going to be delays. But now that I have the part in hand, it looks fantastic. I couldn't be happier with the final surface finish, the quality of it. The threads all work perfectly. There's no debris or any problems with threads. The bolts just threaded right in. And the look of it and the fit of it is exactly what I would have expected. So everything is perfect, and I can't thank PCBWay enough. Now, if you are looking for CNC machining services or sheet metal fab or 3D printing, injection molding, or obviously circuit boards, which at this point we've done a couple projects with them, I do highly recommend PCBWay. You obviously can make your own decisions, but I've been really happy working with them in the capacity that I have the past year or so. If you have any questions on that, please let me know. But let's go ahead and let's take some final looks at the parts on the bike and make sure that we can sort of circle back on what we did. So this process, there are obviously a bunch of different ways that you can approach it. If you don't have a 3D scanner, then you can take some basic measurements. And all you really need to know is the diameter for the stem, the diameter for the forks, and the distances between those three things. And the rest of it you can make up and make your own variation of it. Now, if you are using a 3D scanner like the MetroX or any other scanner, then there are obviously a couple of extra steps in the process. There are things that make the process go easier, like scan spray and prepping your part. If you don't prep it, then you do have to deal with some extra noise in the scans. But we still were able to get a nice, high quality scan that had all the information that we needed. Had I spent a little bit more time prepping the part and had I used it with scan spray, the quality of the scan would have been quite a bit better. Again, we did scan with full field mode as well as a laser scanning mode, so we could understand the differences between those. We took the scan into Revoscan for all the processing, and then we took it from Revoscan into QuickSurface Pro or QuickSurface Lite. Either will work the same in this case. We extracted some primitives, we aligned it to our coordinate system, and then we sent it on to Fusion for the final modeling. Now, if you did follow along with the scan and you wanted to use it, feel free to use it. It's off an 89 GSXR 750. It's the last of the conventional forks for those bikes. Aren't very many of them out there still that still have the conventional forks. A lot of them have been converted to upside down if they still exist. But it is at least good practice for designing these types of parts.
So at the end of this process, we have a nice CNC machine triple clamp that allows us to raise the front end of the motorcycle another inch by dropping down the forks in the clamps. And at the end of the day, that's really all we need to do is make this custom part to help us get a little bit more ground clearance, a little bit more rake angle, and a little bit more trail back on this bike. Now, if you enjoyed this content and you want to follow along with all the rest of this series, make sure that you do subscribe to this channel. We're going to be releasing each part of this series as a sort of basic overview and then a step-by-step walkthrough so you can follow along whichever piece of content you want. And if you have any questions on this or anything else, please leave a comment and let me know. And I also want to thank our sponsor PCBWay for this video, who helped us out with the CNC machining of this part. So once again, if you have any questions or comments, leave them below the video. And as always, thanks for watching, and we'll see you in the next one.